Hello there. This is post-production me. I kind of want to take the time before you get into this video, um, to say what's going on. I am currently editing this or finish editing this in the last day of 2021. I don't know if you can see it, but like at the tiny bottom right corner, there is the date. And I just want to take the time and say Happy New Year's to you guys. Even though this is New Year's Eve, but I'm probably gonna upload this in midnight. Um, and yeah, hopefully the new year is will go well for you guys. If you're watching this sometime past New Year's Eve or New Year's Day, well, hopefully your year is going well. If not, well, it will always get better. It can get better. It's just a matter of, you know, just putting your effort into doing all this. But yeah, I also want to take the time to apologize the inconsistency of uploading these videos. Granted, I am a student attending college, and I just finished my semester. Not to mention that I'm currently in winter break with or in my parents' house. So yeah, I don't really have the time to really record these. I kind of wish I recorded some of these beforehand so that way I could just edit them and then upload them. But I mean, you live and learn. But yeah, hopefully come the upcoming spring semester, I can be more consistent with these uploads. It'll probably won't start till probably like mid to late January. Um, and then from there, I will do my best to have a consistent schedule, probably uploaded on weekends. If not, probably like in the middle of the week. But I mean, I'll see how that goes. In the beginning, it might fluctuate between when I upload them to see what works best for me, but eventually it's gonna be consistent towards the rest of the next year. Um, so yeah, I also want to take time to thank you guys for watching my videos. I do put in quite a lot of effort into doing these. Hopefully you learn something out of these. If not, then feel free to let me know how of a terrible job I'm doing. Yeah, I'll see if I can do any better. Um, but I mean, keep in mind I'm a student in college, so I'm just doing the best I can in sharing this knowledge or this information that I have to you guys. There is other things that I do want to do aside from linear algebra. Some of them include differential equations and then probably physics. I'm not sure how that's gonna go, but I don't know. It's just something that I have in the back of my head that I might want to do. But for now, it's just solely on linear algebra. Hopefully, this series is done by the end of the semester, of my spring semester. If not, probably uh of the following June of that year, I guess 2022. For you guys that are watching this in the future, um the series will probably be done, and then you guys have the luxury to just kind of like skip around and go with whatever you need help on. For those of you that are just hanging on, waiting for me, kind of kind of feel bad for you. I apologize, but just bear with me, and um I'm sorry. But yeah, again, thank you for taking the time. I might actually put a something to like skip if you just want to skip all of this. So probably don't care. That's fine. Fair enough. For all I know, you could just be trying to cram, and that's how it be. But yeah, like I mentioned, cheers to a new year, and happy New Year. Yeah. All right, guys. I'll see you in the next time I do this. For now, I'm gonna go back to the past. All right, let's get to it. Onward with the video. Welcome back to another linear algebra video. It's been a long time, but finally back. This time we're gonna be looking over inverse matrices. I know I said it was gonna be inverse matrices and determinants, but that's gonna be two separate videos. So we're gonna start with inverse matrices. But before we start, let's have a little review with matrix arithmetic. So a couple of videos ago, I mentioned that you can add or subtract two matrices that have the same dimensions. Another thing I mentioned is that you can multiply a matrix by some scalar constant. And lastly, we can multiply two matrices if they satisfy a certain condition. And that's it. That's all of matrix arithmetic. I never mentioned anything about dividing. So, what about dividing? Can you divide two matrices? No. There's no such thing as dividing. You can't really divide two matrices. To begin with, it's already complicated enough to multiply two matrices. I mean, for starters, it has to meet some weird condition, and then even if that condition's met, it's not as simple as multiplying the two elements. No, you kind of have to do some dot product. It's just like, it becomes a lot of work. But there is this thing that we can do that's kind of like dividing, and that is multiplying a matrix by its reciprocal. This is also known as the inverse matrix, and this is pretty much the closest thing you can get to dividing. So we're going to discuss more about multiplying a matrix by its inverse. And so before we do that, we're just going to change the topic a little bit and look at this under an algebra's perspective. So when you multiply a number by its inverse, you get 1. So if you multiply 3 times 1 over 3, that's equal to 1. 4 times 1 over 4, that's equal to 1. This is also like the same thing as dividing that number by itself. So like 4 divided by 4, that's equal to 1. 3, not 3, let's do 5 divided by 5, that's 1. And this is the reason why I can say that this is kind of like division, but at the same time, you're just kind of multiplying by its inverse, so it's not really 100% division. And so going back to matrix algebra, it applies with multiplying a matrix by its inverse. If you multiply a matrix by its inverse, we get the identity matrix. For those of you who don't remember, an identity matrix is a square matrix where its main diagonal consists of 1. And we denote our inverse matrix by raising that matrix by -1. So we have our a raised to -1 over there. And that's the proper way to write the inverse. If you put 1 over a, then yeah, you're kind of weird. For starters, that's kind of like too much work and it takes too much space. But this is the actual like proper notation of writing an inverse of a matrix. And like I mentioned, when you multiply its matrix by its inverse, you get an identity matrix. And one little neat thing about an identity matrix is it's the only matrix that is commutative. So that means if you multiply a times I, that is actually the same as multiplying by I times a. And that's something that is not consistent with matrix multiplication. We proved a couple videos ago that a matrix A times B is not necessarily the same as B times A. And so what we can think of our identity matrix, as I mentioned before, is we can think about the identity matrix as our 1. Because if you multiply by any matrix, you get the same matrix back. And this becomes useful because you can use this in systems of equations. You can find the solution to a system of equations with matrix inverse, or the inverse of a matrix. I mentioned a couple of videos ago or last videos, that we could do it in terms of Gaussian elimination. But another way we can do it is just multiplying the matrix by its inverse. However, it is a special case. The reason being is because the matrix has to be a square matrix. So what ends up happening is, as you have here, we have the inverse of A multiplied by the column vector X is equal to the inverse of A multiplied by the column vector B. And then, as you mentioned, that the inverse of a matrix times the original matrix is just the identity matrix, which is just 1. So we're just left with our set of solutions, which is X, equal to the inverse of A multiplied by the column vector B. And so how do we find these inverse matrices? And that's pretty straightforward. However, as I mentioned before, the matrix has to be a square matrix. And I mean, that's why identities exist. The identity only exists in square matrices. You could have an identity for a 2x2, 3x3, 4x4, and so on, but you can't have one for a 2x1 or 3x2. So inverse matrices have to be square matrices, and to find them, you have to do what is called extreme row reduced echelon form. Extreme as in, like, it's just another matrix. As I did it with Gaussian elimination with an augmented matrix, we had a matrix on one side and then a column vector on the other. Extreme row reduced echelon form is just an augmented matrix where the left side is a matrix and the right side is another matrix. And the only difference is the left side is just a regular matrix, but the right side would be its identity. So if the A is a 3x3, then we have the identity of a 3x3. If it's a 2x2, the identity will be from a 2x2. And so what we want to do is we have to turn or make the inverse matrix on the right and move it to the left side of the augmented matrix. And then our result on the right side would be our inverse matrix. And that's pretty much it. That's how you find an inverse matrix. However, a couple slides I did have a little star on inverse matrices, and because there is an exception. Not all square matrices have inverses. So just because a matrix is 2x2 or 3x3, 7x7 doesn't mean it has an inverse matrix. To have a inverse matrix, its rank must equal to the number of columns, and the determinant has to equal to 0. This is a more formal way of saying this, that a square matrix is invertible, which means it has an inverse if and only if the rank of A is equal to n, which is the number of columns, and the determinant is not equal to 0. If it's equal to 0, it has no inverse. If its rank is less than the number of columns, it has no inverse. And I will discuss further what a rank is at a short little video. But other than that, that's pretty much it. I will do a couple examples on finding the inverse, and from there we'll just move on with determinants. So yeah, I'll see you guys in the Blackboard.